We're going to discuss now a slightly more interesting example in which we're doing a mixture of bivariate normals. And this particular code is set up so that you can easily expand it to work with a mixture of n-variate normals if you want. And you can also easily change the number of components that are involved. One word of warning is this particular code uses these two libraries called MBT norm and ellipse, which you can easily download from CRAN, but make sure that you have installed the libraries before you try to run the code. Okay, so the structure of this code is very similar to the one we saw before with the mixture of univariate normals. So we're going to work with bivariates, so that's what the p parameter controls, is that we are bivariate normals. Again, we're going to work with 3 components in the mixture, and we're going to have the same epsilon parameter that controls when to stop the algorithm. That is going to be 10 to the minus 5 again. So we are again going to work with simulated data. In this case, however, rather than having the same variance-covariance matrix for all the components, we're going to allow both the data that we generate and the model that we fit to have different variance-covariance matrices for each component of the mixture. So the setup, again, is very similar. So we still have 3 components with weights 0.5, 0.3, and 0.2, just like before. The means for the normal distributions are, and because these are bivariates, now I need to report vectors of means. So the first mean is 0, 0, the second mean is 5, 5, and the third mean is minus 3 and 7. And finally, I have 3 different standard deviations for the true data. The first one is just a diagonal. It's the identity variance-covariance matrix. So this one is just the identity matrix for the first component. But in the other components, we have, in the first case, variance-covariance matrix that is non-diagonal, and in particular where the variables are positively correlated. And for the second component of the mixture, we have a case where the variables are negatively correlated to each other. So this is a situation where the data has this form. This is a situation in which we really don't want to use a mixture model that forces all the variances to be the same. So again, we set the seed so that you can reproduce the results that we're going to show. We again work with 120 observations, and the structure is very much the same. So we first select which components each observation belongs to, and then we generate the observations accordingly from that component. In this case, we also generate a plot of the data in the distributions that we're working with. In this case, because this would be a 3-dimensional plot, rather than plotting the density itself, we're going to plot some contour plots for the density. So let me execute these commands. And you can see in this case, I'm showing these are the true observations, so the data. And again, I use colors to differentiate which observations come from each component. You can see that in this case, this observation 58, it's green, so it's coming from this mixture component, but it's actually a bit of an outlier for this distribution, and it kind of looks a little bit like it overlaps with the black dots here. So we will actually see a little bit what happens, or we will use this observation as a test case at the end to, again, highlight a little bit how the algorithm works. So this is the true component, so the contour plots of the true density with the points that we have generated. And then, as in our previous example, we have a guess at what are the values of the parameters to initialize the algorithm. And as before, we are assigning a weight of 1/3 to each component. We are selecting means randomly. And in this case, I'm using, again, the variance of the data to have a guess of what the variance of each component is. But in this case, rather than using just the raw variance, I'm dividing it by the number of components. So a way to think about this is by assuming that you are splitting, in some sense, the variability of the data into as many components as you have and saying that the variability is very similar. But again, these are just initial values for the parameters. The algorithm will refine that. And this is the code that generated this graph that you can see here with my initial guess of what the variances of the different components is and the location of the different components is, overlaid with the location of the actual observations. And you can see that my initial guess is not a terribly good one, but again, don't worry about it because the algorithm will refine it. So once we have provided initial values for the algorithm, the structure is very much the same. So we still have the switch variable that allows us to stop the algorithm once we decide that we're close enough to the solution. And KL is our metric of how close we are to the solution. We have the E step and we have the M step. The form of the E step is exactly the same that we had before. The only difference is that we replace the normal distribution with this DMB norm because it's a multivariate normal now. But otherwise, it's exactly the same expressions that you saw before. For the M step, the weights are also computed in exactly the same way as in the univariate case. What changes a little bit here is that now the values of the mu's are vectors, so I need to do the sum over vectors rather than over scalars. And that before we had kind of a separate loop for the sigmas because we had a single value of sigma for all components. Now we have different sigmas for each member, so the structure changes a little bit. But you can see that the formulas are very, very similar to the ones that we saw for the univariate case with same variance for all of them. Again, we check convergence in pretty much the same way as we did before by computing this expected value of the complete data log likelihood. And as before, we also present at each iteration these two results. So a figure similar to this one, where we show where the current guess of the components are with respect to the data, and a running plot of this fitness metric. So let's run this algorithm. In this particular example, it took only 12 iterations for the algorithm to converge. It was much faster than in the previous example. And again, let's look at this as a little bit of a movie by just scrolling through the different components. So this is where we started. This was our initial guess at what the components of the mixture are. After a single iteration of the algorithm, you can see that the variance, at least for these two components that were up here, kind of has expanded quite a bit. And that makes sense because in our initial guess, basically there was no way to explain these green dots up here. So so the first step of the algorithm is just to say, oh, something needs to grow in order for us to capture these observations that are up here. So that's the first thing that the algorithm does. And then as you move along, you can see that it's starting to kind of refine. It's starting to separate these two components that are up here. It's starting to say, well, they don't really have the same mean. They need to kind of move apart from each other. And it does it slowly, but surely. And you can see how now it's starting to realize what the centers of those components are. And now it's starting to converge pretty fast. We're up to iteration 8. And now what it's doing, it's basically slightly refining the structure of the mixture. And one thing that should be clear if we compare this graph against the very first one that we had is look at the contour plots for the green dots. They end up way short of the contour plots for the black dots, unlike in our original graph where we could see that these two were very close to each other. A consequence of that is that now this green dot that was a little bit of an outlier when we were discussing the original data, now it's roughly being classified in this black component. And we can see that in two ways. So first of all, we can see the value of the vector b. So let's do the following. First, let's look at the means of each one of the distributions. So if you look at the means of the distributions and you compare it with the true means, you can see that again we kind of have flipped the labels. So 0, 0, that was component 1, is now component 3. 5, 5 is still the second component. And minus 3, 7 is now the third. It's now the first component in the mixture. So we have kind of flipped the order just like in the previous case. So if we look at the vector b in row 58, remember this is giving me a guess of which component each observation belongs to. And 58 was the observation down here that we kind of had misclassified in the beginning. Observation 58 was generated, we know, by this component, this green component that has mean minus 3, 7. But if you look at what the model is saying, the model is saying that the heavier weight for that observation, the largest b, it's on component 3. And if you look at what the value of mu is for component 3, that is 0, 0. So in other words, the algorithm is saying that observation really it's more likely generated by this component down here than by the component, the green component up here. And what that does is that at the end of the algorithm, it somewhat underestimates the variability associated with the green component because this point is now doesn't belong here, it belongs down here, which means that a lower variance can explain what is happening with the green dots. So, but aside from that point that is a little bit and was a little bit of an outlier in the beginning, all the rest of the points seem to be properly classified by the algorithm.